Okay, so good evening everyone. I am Shivani Dhok and I welcome you all for the week 4 tutorial for the course of simulations of communication system using MATLAB. So like every week, this week's tutorial will also have two parts. First will be recap of week 4 content and followed by some questions which are related to week 4 content. So let's start with a quick recap of week 4 content. So week 4 was all about generating random variables. Okay. So we said that in MATLAB when we are generating random variables, basically we will be generating what is known as a pseudo random variable. So we will be generating pseudo random variables. And by that, what do we mean? So MATLAB will generate something like x of n equal to a x of n minus 1 plus c mod m, where we have x0 as seed, which is basically depending on what time we are operating, and the nth random variable will be xn by m. So like that, a random variable is generally obtained, and we select this a, c and m in such a way that this xn is a uniform random variable. It will give me a sequence of random variables that will be uniformly distributed. Now this uniform random variable, if we have a continuous distribution, this uniform random variable, which we can represent as, let's say, from 0, uniform from 0 to 1. So this thing has a PDF as 1 for x. Sorry, let me. Okay. So we have this uniform random variable. So let's say a random variable x is distributed uniform in interval 0, 1 if its PDF or probability density function is given by fx of x is equal to 1 if x belongs to 0, 1 and 0 otherwise. And the way we generate this uniform random variable is through this rand command, that is rand. So how does this command work? So let's quickly look at that. Sorry. Yeah. So this is my MATLAB screen. Okay. So we want to use this rand command. So we'll just check or get a help on this command, that is rand, and it gives me some details. So it says that this will generate uniformly distributed pseudo random numbers between 0 and 1. So if we say n cross n, rand of n, then it will generate n by n matrix containing pseudo random values, and these will be uniformly distributed on the open interval 0 and 1. Okay. So for example, if I write rand of 3, it will generate a 3 cross 3 matrix like this. It will be random. Every time I run, it will be a random variable or randomly generated, or to be very precise, it will be a pseudo random variable. And if I want to generate n variables, let's say 10 comma 1, so this will give me a column vector of dimension 10 cross 1. And if I generate, let's say, lot of them, So okay, it will take time. Okay, so it's taking a lot of time. Let's not waste time here. I'll just close this MATLAB and open a new one. Hello? Hello? Am I audible? Hello? 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 Am I audible?
Audible, ma'am.
Okay, thank you. There was some issue with my mic. Now it's fine, I think so. Let me share my screen. Yeah, okay. Yeah. Okay, so we saw how to generate these uniform random variables. Another thing that we looked at was generating discrete uniform random variables. So this rand I command here, so this rand I command will basically generate discrete uniform random variables. So what does it mean? So if we have a set, so let's say this random variable x can take value from x1, x2, x3 and so on till xn, and probability that x takes value xi will be equal to 1 by n for all I equal to 1, 2, 3 and so on till n. So this is the discrete uniform random variable that can be generated using rand I. So for that we considered a small example, that is this coin toss model. So in this coin toss model what we considered was the probability of getting a head and probability of getting a tail was equal to half. So we can simply generate it by using rand I of 0, 1 and whatever number of samples we want. Something like this we can use it. So let's look at it quickly. So this is x equal to rand I. Let's say we want it from 0 to 1 and then we will take, let's say, 1000 values of them. So here we have x which is either 1 or 0, something like this. And now if we just do histogram of x, so we see that almost 5, we had 1000, so almost 500 number of or let's say 512 elements of those vectors are basically 0, and again remaining are 1. Okay, so if we check, the number of ones in this list will be is 488, sorry, 488, and number of zeros will be simply like this. So we have 512 zeros and 488 ones in this list. So as I increase the number of samples that I have, this proportion will become more and more close to half. So let's say P1 equal to sum of x divided by 1000, which is 0.5059, and P2 will be, let's say P0 will be 10,000 minus sum of x. So that is also close to 0.5. So it generates 0 and 1 with probability half. So that is the use of this randi command. So let me add a page after this. Yeah, okay. So then we considered selecting an element of a list uniformly. So an example, a similar example that we took was, I have a list, let's say E by, then let's say Boltzmann's constant, etc., and we want to select some elements from this list uniformly. So let's say this list is L. So what we considered was, or the way we did it was, we'll use uniformly generating discrete random variable through randi. So we'll generate the index which we want to access through this, and that will be randi into length of the list. That will give me an index, and then my random variable x will be simply length, or this L that is available at the index idx. So this is the way we will be accessing a list, or taking or select uniformly an element from the given list. After that, we looked at Gaussian random variable. So this Gaussian random variable is very important random variable when we come to communication systems or any other system. So a random variable x, or a continuous random variable x, is distributed Gaussian with mean mu and variance sigma square if its PDF is given as fx of x, which is equal to 1 upon under root 2 pi sigma square into e power minus x minus mu square by 2 sigma square, and this x belongs to my entire real line. So this is the PDF for a Gaussian random variable, and the way we generate this Gaussian random variable in MATLAB is through this rand command. So this rand command will generate a Gaussian random variable with mean as 0 and variance as 1. So this is known as standard normal. Okay, so let's quickly see how it is done. Okay, so let me just close this variable space also. And so let's say x is rand, and let's say what we do is we want, let's say, 1,000 values of it. Let's construct a column vector. So this is what we get. Then we'll do f comma x equal to, and within we'll plot, sorry, not rand n. Okay, so this is how it is looking. So let me just quickly increase the number of samples. So as you increase the number of samples, it will become more and more Gaussian. And if we find out its mean, it is close to 0. And if we find out its variance, it is close to 1. So basically it is generating a standard normal random variable if we use randn function. I think I made some mistake while, yeah. So this thing here will be randn. So basically what we want to do is we'll take rand n and dimension. And after that, we looked at what is known as rand perm. So this rand perm basically generates, so it generates a random permutation of a sequence. And if we do rand perm of n, so sequence 1, 2, and so on till n. So it will generate a random permutation for this given sequence. After that, we looked at histograms. So these histograms are basically frequency versus bin centers, or it basically plots the frequency of whatever elements we have. So we generally plot it as frequency versus bin centers kind of things. And it helps us in visualizing the PDFs. Or let's say PMF. After that, we looked at how to generate distributions using using uniform random variables. So what we said is, let's say we want to generate a random variable x with CDF fx. So what we do is, and we want to do it with the help of uniform random variables. So what we do, we generate u which is uniform in 0, 1, and then this x will be given by fx inverse of u. This is the way in which we will generate any random variable with the help of only uniform random variables. Okay, and we looked at the examples to generate different random variables using this, and the first one was exponential random variable. So this exponential random variable, let's say x, which is exponential with parameter lambda, has a PDF fx of x equal to lambda into e power minus lambda x for x greater than or equal to 0, and its CDF fx of x is simply 1 minus e power minus lambda x. So this x we can generate. So this x we can generate as fx inverse of u, where u is uniform in 0, 1, and this can be simply obtained as minus 1 by lambda into natural log of 1 minus u. So this is the way we will generate an exponential random variable. After that, we looked at a very important distribution which is very useful when we go for communication systems, wireless communication systems, and that is known as complex Gaussian random variable. So a complex Gaussian random variable takes the form x plus jy, in which x and y both are Gaussian. And a special case of this Gaussian random variable is what we call as circularly symmetric complex Gaussian random variable. So basically, let's say this is Z. So in circularly symmetric complex Gaussian random variable, what happens is this variance of x is variance of y is equal to variance of z by 2, and this x and y are independent. Okay, this is circular symmetric complex Gaussian, and we also saw that how to generate these using uniform random variables, and for that we used the polar coordinate representation of this same random variable, that is r into e power j theta. And for a circularly symmetric complex Gaussian, this r is Rayleigh distributed, and this theta is uniform in minus pi to pi. And we looked at how to do or how to generate these. We'll take an example when we are solving questions. That will be much more clear. After that, we looked at what is known as Bernoulli random variable. So this Bernoulli random variable is very simple. So it takes value 1 with probability p, and it takes value 0 with probability 1 minus p. So this random variable x is called as Bernoulli with success probability as p. And then we have binomial random variable. So this binomial random variable is binomial NP, and it says that its PMF, where x takes the value k, is simply given by nck into p to the power k into n minus, 1 minus p to the power n minus k, and this can also be written as sum of IID Bernoulli's with success probability as p. Okay, so these are binomial random variables and Bernoulli random variables. After that, we looked at two important theorems in probability, or two important concepts in probability theory, which is law of large numbers and central limit theorem. So in lecture, the law of large numbers was specifically stated for Bernoulli random variables. I'll just state it for general. So if we have x1, x2, and so on till xn as IID random variables, such that expectation of xi is mu and it is less than infinity, then Sn, which is defined as summation of I equal to 1 to n xi, we have limit n tending to infinity Sn by n minus mu goes to 0. And when we in lecture, it was specifically mentioned, we did it for Bernoulli, for which expectation of xi was equal to probability that xi equal to 1, which comes out to be equal to p, and this specializes as limit n tending to infinity Sn by n minus p goes to 0 as limit n tends to infinity. After that, we looked at another interesting result, which is known as central limit theorem. So it's a wonderful theorem in the sense that a summation of all IID random variables will converge in distribution to a standard Gaussian random variable. So this is an interesting result and very useful result in a lot of applications, including in wireless communications. So it states that these are important concepts, so that's why I'm repeating them. So x1, x2, x3, and so on till xn are IID. IID means independent and identically distributed random variables with mean mu and variance sigma square. Then summation of I equal to 1 to n xi minus n times mu. So basically this will make the mean of this particular quantity as 0, and now we want its variance to be equal to 1. So for that we'll scale it by under root n into sigma. This will converge to a standard Gaussian random variable, and this convergence is in distribution. So this is the central limit theorem, and with this we ended the first week's content. If you have any questions, please let me know. Otherwise, I'll move on to the part where we'll be discussing questions which are related to this week's content. Another thing is, if you have any questions, then please unmute yourself because I am not able to see the chat box. Okay, if there are no further questions, then let me quickly move on to the questions section. So like every week there are 10 questions, and this time out of 10, the first 5 are from the previous year's assignment, and remaining are some additional questions which might help you in solving the coming assignment. Okay, so let's start with the first question. So the first question says that given that the random variable y is generated like this, that is rand I 1, 0 and 1000, 1 in MATLAB, what is its physical interpretation? So what is given to us is some random variable generation using rand I. So once we have this rand I coming into picture, one thing that we know is we are playing with integers. So this I here is indicating that we are playing in integers. Then the first argument that we have in this rand I is 1, 10, and this indicates that we'll be generating random variables, or let's say integers. Just a minute. Integers between 1 and 10. And then we have another input to this command, that is 10,000 comma 1. And this thing here indicates that generate random variable or random vector with dimensions 10,000 cross 1. So let's now see what options we have. So the first option that we have is there any question? Okay.
Ma'am, dimension का मतलब है
Sorry.
मतलब you understand dimension?
Sorry,
Dimension.
your voice is not clear, ma'am.
What the dimension indicate?
This indicates the dimension. This indicates the dimension. So that is 1,000 cross 1. So it will generate 10,000 cross 1 dimensional vector.
Means the space is so much segregated.
Your voice is not at all clear. Can you type what you're saying in chat box? I'll refer to it now.
Here. So,
Yeah.
in dimension, what is the literal meaning of dimension?
Okay.
For
What
the
is the literal meaning of dimension? Okay, I got it.
communication between.
Yeah, okay, one second. So dimension means, okay. So matrix, or let's say MATLAB, I'll add a page here. So MATLAB works with matrices. Okay, and matrices, any matrix A will have m rows and n columns. So when I refer to dimensions, so here when it is said that I'll generate a random variable with dimension n comma m, then it means that I'll have a random matrix with n rows and m columns. So if for example here, when it is mentioned I am having 10,000 cross 1 as dimension, so this command will basically generate a column vector of dimensions 10,000 cross 1. So for example, I'll just show it in MATLAB.
Okay, then we have to generate 1,000 random variables in the range of 1 to 10.
Correct.
Thank
So
you.
I have this, I'll just rewrite that command. Yeah, so this was the command that we are having. So okay, let me just, will mess up with. Okay, so if you look at my workspace, what it is doing is it is generating a random vector which has dimensions here as 10,000 cross 1, which means it is a column vector. So if you see, it's a column vector like this. Now suppose I generate another random variable, let's say y, with rand I, same thing, comma 1 comma like this, So now if you see, its dimension is 1 comma 10,000. So if I open it, it will be a row vector like this. So it will be a row vector of 10,000 1 comma 10,000 dimension. Similarly, if I generate, let's say 10 comma 10, let's take a small matrix like this. So this Z, or let's say for that matter, just take 2 comma 3 like this. So if you see, it is a 2 cross 3 dimensional matrix with 2 rows and 3 columns. So if I say the dimensions are m cross n, it means it will generate a matrix with number of rows as m and number of columns as n. Is it clear, ma'am?
Yes, ma'am.
Okay, thanks. Any other questions? Okay, so this x was the one which was given to us in the question. So let's see what exactly it is giving. So if you see, it has integer values from 1 to 10. Okay, so if we just try and plot its histogram, that you can simply do by right clicking here and histogram of x. So if you see, it is uniformly generating the values from 1 to 10 only and nothing else. Okay, so the answer to our question here will be, it is length 1000 vector containing random integers below 10. Okay, and someone had mentioned that the option D will be the correct answer. It says that it is a list containing 10,000 random real numbers between 1 and 10. It's saying real numbers. It won't generate real numbers, it will generate integers. So this rand I will only generate integers and not real numbers. So that needs to be very clear, when to use rand I and when to use rand and all those things. So just be very clear that it will generate integers and not uh, real numbers. So the correct option will be B. Any other questions? Okay, if there are no questions, then let me move on to the next question. So this is also a question from last year's assignment. So it says that given a chi-squared random variable with k degrees of freedom, it is a sum of k IID random variables, or yeah, I forgot to mention k IID Gaussian random variables, KID Gaussian random variables with k degrees of with zero mean and unit variance. So we want to write a MATLAB code to, again, KID sum of square of, yeah, KID Gaussian random variables with zero mean and unit variance. We want to write a MATLAB code to generate a sequence of random variables with k degrees of freedom. So okay, so what we want to do is, we want to generate a sequence of, or let's say n chi-squared random variables k degrees of freedom. And we have been given the definition of a chi-squared random variable. So x is chi-squared random variable when if we, or it is a chi-squared random variable with k degrees of freedom if we add k IID, or if we add the square of k IID Gaussians. So here these xi's are standard normal with mean 0 and variance 1. So what we need to do is, or by looking at this particular information, what should come in our mind is, first we need to generate k Gaussian random variables, and then get chi-squared random variable from it. Okay. Okay. So let's say, and in order to generate a Gaussian random variable, so for a Gaussian random variable, or for generating n01, the command that we can use is rand_n. Okay. So what we will do is, step 1 will be generate a matrix X1 which will have n cross k standard Gaussian entries. And how can we do that? So we can do that by writing x1 as rand n comma k. And after that, what we want is get x, which is n cross 1 chi-squared random variable. So now what is happening is, at this particular time, we have an n cross k dimensional Gaussian random vector, and we want to sum the square of entries in each row. So for that, what we can do is, we can simply do x equal to sum of x1 element wise square, comma, we want row wise sum. So this will give me an n cross k dimensional chi-square random variable. So let us quickly see that in MATLAB to understand it better. Okay. So let me just clear the space. So first step we need to do is, or let me add a script for that. So first we need to get n, let's say it is 1e plus 3. What is its number of chi-squared random variables? Then let's say k is for now 5, and this is the degrees of freedom for chi-squared random variable. So what we will do is, step 1, generate n cross k IID Gaussian matrix. So that can be done by x1 equal to rand n comma k. So let us quickly run this till this part if it is correct or not. So this is for chi squared. So if we do that, we get x1 as 1000 cross, so you can see 1000 cross 5 dimensional Gaussian vector. And now what we want to do is, in order to generate a chi-squared random variable with 5 degrees of freedom, we want to take the first entry, square it, then second entry, square it, third entry, square it, fourth entry, square it, fifth entry, square it, and add all 5 of these. So we want to add, so first random variable will be sum of squares of your first row. Second random variable will be sum of squares of your second row, and so on. Similarly, your 14th random variable will be sum of squares of your 14th row's elements. So what we want to do is, step 2, get chi-squared random variable, and for that what we will do, we will element by element square it.
So why we get 1000 entries,
Sorry,
1000 rows? We are
because
getting 1000.
we have specified the number of rows as 1000. See, this is the number of rows that we are specifying. So when I'm using this rand n comma k, so this n is the number of rows that it will have, and k is the number of columns that it will have. And this 1e plus 3 is a way of writing 10 to the power 3. So if we write 1e plus 3, that is simply 1000. So that is a way of writing 1000. So, and if you take, if you won't understand what is happening, you can write help rand n. So what it will say is, so if you say rand, second, rand m comma n, rand n m comma n, or rand n like this, it will return an m by n matrix. So that only is happening here. So
Fine.
here n is 1000, so that's why I'm getting 1000 rows. So number of rows is n, that's why I'm getting 1000 rows, and k is the number of columns. That's why I'm getting 5 columns. Is it okay? Okay, so once we have this Gaussian random, hello? Okay, so once we have this Gaussian random variable, do you have any further questions, ma'am? If not, please please mute yourself.
Okay.
Please unmute once whenever you have questions. Okay, so we have this Gaussian random variable, and as I mentioned earlier, we want 1000 chi-squared, and we want element by element sum square of these, and then add it row wise. So what we'll do, we'll first take element wise square, and then we'll take sum, or row wise sum. Okay, so for that what we can do is, let's do it step by step. Let's say x1 is simply x1 square, and then we want x as sum of x2 comma, we want the dimensions, that is 2. And if we do that and run it, it will give me a x as a chi-squared random variable. And if you want to check if it is correct or not, this is simply sum of squares of each row. So let's say x1 is x1 first row and all columns, So it will simply give me the entries from the first row, and then you can simply do sum of x1 square. So that will give us the exact same entry that we are getting here, that is 12.4175. So this is the chi-squared distributed random variable. Again, these two steps which we considered here, we can simply merge them in one step. That is, we can write it like this. It will again give me the same thing, but this is more memory efficient. I'm not allocating additional variable for doing this squaring operation. So again, this will be a chi-square random variable. Just for simplicity, we'll see, just for understanding, we'll just see its histogram. So it looks something like this. I won't go into more details of the PDF and CDF of this chi-square random variable, but yeah, we generate chi-square random variables something like this. Any other questions at this part?
But why is the entries from x comma 2? Why we don't take it once?
This one
We have single column now.
here,
We have single. Why we take it 2
because we
sum of
want
x two
row wise sum. Okay, so
because we want
let's say I have a matrix A, 1, 2, 3, 4. Okay, so if I take sum of A comma 1, it will do column wise sum. So it will give me 1 plus 3, that is 4, 2 plus 4, that is 6. Now if I do sum of A comma 2, that will give me row wise sum, that is 1 plus 2, that is equal to 3, and 3 plus 4, that is equal to 7. So when I have this Gaussian random variable x1 here, I want row wise sum, not column wise. I want it to be squared and summed up row wise like this, and not like this. So in order to specify clearly that I want it row wise, I am writing it as 2 here. Is it clear?
find.
Okay, if there are no further questions, then let me move on to the next question. Okay. So this is the third question. It says that which of the following commands can be used to generate a binomial random variable with parameters np? Now what we had seen earlier was, or when we were discussing the content, we had said that a binomial random variable, let's say x, I can write as summation I equal to 1 to n yi, where yi are Bernoulli random variables with success probability as p, and then this will give me x as binomial n comma p. Okay, so now what we need to do is first, so if we understand this part, what we need to do is first we need to generate n Bernoulli random variables with success probability p, and that we can do using rand command. So that we can do by considering rand, and how many do we want? N comma 1, and then we want these to be, we want, this is the way we do it. Then we have double, so this will give me n Bernoulli random variables, and once we have these, then we need to sum them up. So my x will be simply sum of double of rand n comma 1 less than p. So this is the way we will be generating Bernoulli random variables. This was discussed in detail in the lectures. Still, I am writing this here. So if we look at the options, the correct option is this one. So let us quickly see if that is correct or not. Okay. So, so this is for binomial distribution. So for that, what we want is get. So we want this binomial distribution with parameter n comma p. So let's decide what is n. So n, let's say, is 10 and p is, let's say, 0.2. So let's get n Bernoulli random variables. Let's say Bernoulli p random variables. And how do we do that? So that we will do by considering x is equal to double of rand of n comma 1, and this thing should be less than p. And just to check if it is correct or not, we'll just see mean of x. So this mean of x should be equal to or should be close to your p, whatever you are setting. Or let's say this, just for now, let me take this as a very large value. Okay. So if you see here, it is close to 2. And if I increase it further, see, this is very close to 0.2. So this will give me a Bernoulli random variable, a binomial random, a Bernoulli random variable with whatever success probability that we want. And after that, we want get binomial n comma p by adding up the n values or n IID Bernoulli random variables. So that will be simply y equal to sum of x. If I run that, let me just increase this to 0.5. Okay, so that will give me some things and that will generate a Bernoulli random variable. Now, just for fun, what we will do is, let's take n values here. Let's say I want to generate n random variables or n Bernoulli random variables. So this will be n comma capital N. So now I want to sum it over the column direction. So that will give me y as Bernoulli random variable and I can again plot its histogram, which looks something like this. So this is my binomial random variable, whose PDF looks something like this. If I take less number of entries, let's say something like this, then it will be something like this. Now if I have this as 100, let's say, and if I take this as a small value, then it will be skewed one. Histogram of y will look something like this. Okay, so again, if I reduce it, then it looks something like this. So this is how to generate a binomial random variable with the help of Bernoulli random variables. So this was discussed well in the lecture, still I took it here. Any other questions in this part? Okay, if there are no questions, then let me quickly move on to the next question. So this question is simple. It just follows from whatever we discussed in the previous question. So it says that this particular MATLAB command, that is double of rand of something greater than p, will generate a dash random variable whose probability of success is so here it should be 0.1, whose probability of success is whose probability of success is 0.1. So now this probability of success is 0.1, which means that here in this particular case you need to set this p as 1 minus 0.1, that is 0.9. So if you look at our previous case, we saw that we want to generate a Bernoulli random variable with some success probability, then we should have a less than term coming into picture. However, this particular thing will generate a random variable, or let's say a Bernoulli random variable to be precise, with success probability as 0.9 if p is equal to, success probability as 0.1 if p is equal to 0.9, or in other words, it will generate a random variable x which will be equal to 1 with probability 0.9 and 0 with probability 0.1. So this we had seen anyway in the previous question. Still, if you have any doubts, then let me know. Okay. Then the next question, let's quickly move on to the next question. So the next question says that x1, x2 and so on till xn are IID Bernoulli random variables with xi equal to, expectation of xi equal to p, and Sn is the sum of I equal to 1 to n xi. Then limit n tending to infinity Sn by n minus p tends to 0. This statement is, so we have seen that this particular thing is definition of the weak law of large numbers. We have seen that. So this is anyway the correct answer. Still, for the sake of completeness, I'll just mention that this strong law of large numbers is a stronger constraint than this particular thing, than the weak law of large numbers. It requires almost sure convergence. I won't go into detail of this. This is beyond the scope of these lectures. this course. But if you want to understand what this is, please look into the good probability courses. I won't go into detail. I'll just mention what it is. Center limit theorem, we had seen that some of IIDs will converge to Gaussian. And then there is this Markov inequality. So this Markov inequality is specifically for a non-negative random variable. So it says that the probability that this non-negative random variable is greater than some epsilon, where this epsilon is greater than 0, is less than or equal to expectation of this quantity or this random variable x divided by epsilon. So this is what is known as Markov inequality. However, the definition what is mentioned here is we have seen it in normal in our regular lectures. It is for the weak law of large numbers. So I just mentioned for the sake of completeness what other options are. If you have any questions, then please let me know. Okay, if you have no questions, then again, if you have questions, please unmute yourself. I am not able to see the chat box. Okay, let's move on to the next question. So again, this was discussed in the lectures. Still, I'll revisit this particular concept. So it says that write a code for uniformly selecting an entry from the following list, which is e, pi, phi, psi, and epsilon. So now what I'll do is, these things cannot be defined like this in MATLAB. So what I'll do is, I'll define them like this. So let's say this is my list. Sorry. Yeah. So this is my list. Let's say list 1, which is something like this. Then this one is psi, and the last one is epsilon. So I'll just write EP for that. So this is my list. This is the way I'll declare this list, or I'll define this list in MATLAB. And then what I want to do is I want to uniformly select an entry from this particular list. So what I'll do is, let's say n be equal to length of list 1. So this will basically give me number of entries in list 1. And after that, I'll pick an index that will be anything from 1, 2, 3, and so on till n. So I want to uniformly generate a value between 1 to n, and that can be done using the function rand I. So I'll take rand I, one to n, and then I'll get my x as list 1 of index or IDX. So this will give me a uniformly selected entry from the given list. Now these three steps we can merge into one command as x equal to list of rand I 1 to length of list 1 like this. So if we do that, we can merge these three commands into one command. Is it clear? Let's quickly do this thing in MATLAB also. If you have any questions at this point, just let me know. Another thing is it's okay if you don't take notes, because all of these things will be available to you through the recording sheet. Okay, so what we have is list 1 as the first entry in our list is E, then the second entry is pi, third entry was pi, fourth entry was psi, and the fifth entry given to us was epsilon. So it is a EPS. And so what we want to do is get the length of list 1. Then we want to get a random index that we can do by using rand I between 1 and n, and then we can get x equal to list 1 of index. So let's run this. So this is an example for uniform selection from list. Okay, so if you see, let me just remove this. So if I run it, it generated as phi. If I run it another time, it will generate something else. If I run it pi, then again if I run it, something else will show up. So uniformly it will generate a value which is there in this particular thing or particular list. I can again replace these three commands into one command, that is x, as list 1, and now we want to get the index, and for that index we'll use rand I, and between what and what we want it, between 1 and length of list 1. Again if I run this command, it will give the similar outputs. Again it is randomly generated, so it won't be exact same, but yeah, this also works. So it will randomly generate or uniformly select an entry from the specified list. If you have any questions, then let me know, otherwise I'll move on to the next question. Okay, so this is the next question that we have. So now it says that what are the possibilities that the rand perm will generate. Okay, so we have seen that this rand perm operation, so this rand perm operation there is some issue, I think so. Just a minute. Okay, so this rand perm operation generates a random permutation of sequence 1, 2, and so on till n. So this random of 5, this will generate a random permutation of 1, 2, 3, 4, and 5. So what is asked to us is how many possibilities are there. So basically we have 5 options, and we have 5, we have 5 ways to do it. So what we can do is the first place can be filled in, just a minute, yeah, in 5 ways. The next can be generated in 4 ways, then third one by then by 2 ways, and by 1 way. So in short, this is 5 factorial ways. So in general, if it is n, it will be in n, it will be n factorial ways. So this can be generated using n factorial, sorry, using n factorial or 5 factorial ways. So this is the final answer. Any questions? This was also done in lectures. I'm just repeating it. Any other questions? Okay, if there are no further questions, then let me move on to the next 8th question. Just a minute. Yeah. So the first question given to us is, how will you generate a Gaussian random variable with mean mu and variance sigma square? First part is using randn function, and second part is using rand function. Okay, so first thing that, let's start with this part. Let's start with the first part here. So what we know is this randn function, generates a standard normal random variable. What does it mean? It will generate this thing. But now what we want a Gaussian random variable with mean, mu, and variance sigma square. So we want x that is generated as something like this, mu comma sigma square. Okay. So now let's do this thing. Now let's say I have a random variable x1, which I write, uh, okay, let's say I have a random variable x1. Sorry, any questions? Okay, let's say I have a random variable x1, which is standard normal, And let's say I have another random variable x2, which I write as sigma of x1, sigma multiplied by x1. So for this particular random variable, what do we have? Expectation of x2 will be equal to sigma into expectation of x1. Expectation of x1 is 0, and we have variance of x2 will be equal to sigma square into variance of x1, which will, and variance of x1 is 1, so this comes out to be equal to sigma square. So at least now we have variance as sigma square. Now what we will do, we'll take this x, we'll generate this x as mu plus x2. So in total, this is simply mu plus sigma x1. Okay, so now expectation of x1, expectation of x will be equal to, mu is a constant, so mu plus expectation of x2, and expectation of x2 we have obtained as 0. Okay, and then we have variance of x, which is equal to, mu is a constant, so it won't affect here variance, so it will be simply again sigma square variance of x1, or simply variance of x2, which is equal to sigma square. Sorry, this is not 0, this is mu. Okay, and linear combination of a Gaussian random variable is simply a Gaussian random variable. So this x is equal to mu plus sigma x1. So now what we have is this x is Gaussian with mean mu and variance sigma square. So how we can do that? We'll generate a random variable x1, which is standard normal. So we started with a standard normal, and that we can do using this random function. And then we'll multiply it by sigma and we'll add mu to it. Okay, so how we will do it in MATLAB? So in MATLAB, this x will be equal to mu plus sigma multiplied by rand n of 1. And if I want to generate, let's say, n cross 1 dimensional, then n comma 1. So this will simply give me n values, or n realizations, let's say values of, or n random variables with mean, mu and variance sigma square. So instead of writing values, I just write random variables. Okay, just let's try to verify if it is correct or not. Okay. So what we want to do is, we want to generate n mu comma sigma square. So sigma mu, where mu is mean and sigma square is variance, and let's say we want n random variables to be generated, and this first way we want to do is using random. And let's say we have mu as 1 and sigma squares or sigma square as, let's say, 2. So what we will do now, we'll and let's say n, capital N, the number of values that we want, or number of random variables that we want to generate. Let's say that is 1e plus 5 or 10 to the power 5. Okay, so let's say we'll go step by step. So we had x as mu plus sigma. It was sigma, not sigma square. So I'll have to take square root of sigma square multiplied by x1, where this x1 is a standard normal. So that I can generate using rand n comma 1. And then I'll have this x. So what we will do now, we'll take f comma x, say f1 comma x1, which is equal to histogram of x with bins as 100, and then let's plot x1 comma f1. Let's run this. Let's name this as get Gaussian. So that will give me a Gaussian random variable with some mean and variance. So let's check what is mean of this, whatever we have generated. So mean of this x is, just a minute, is close to 1, which we wanted, and the variance of x should be close to 2. So okay, this is again close to 2. We can increase this, the number of values that we want, to let's say 10 raised to 7. So this PDF now becomes very smooth. And then what we can do is we can again see what the mean is. So it is 0.9992. It is very close to 1. And then we can also find what is variance, which is 1.9997. Again, it is very close to 2. And the PDF is anyway Gaussian, that we have seen. So the way we generated Gaussian is using a standard normal random variable through randn. We'll add a mean and also we'll multiply it by sigma to have the required variance. So this is a standard way of generating Gaussian random variables using a standard normal random variable. Is it clear? Any questions at this point? Okay, if there are no questions, then let me quickly move on to the next question, or the next part of this particular question. Let me add a page. Okay, now we will look at this thing, randn or rand, how to use it, how to generate it using rand function. So this rand function generates uniform in 0 1, and using that we want to do this. So what we will do is we'll try to generate, or step 1 we'll do, we will generate n01, or let's say x1, which is like this, 0 1, using rand. And for that what we can do is we can write this x1 as r into cos of theta, where this theta is uniform in minus pi to pi, and this r is Rayleigh. Okay, and we want this to have a unit mean, which means that this r square should be exponential, and this should have mean as 2. Okay, which means that so this should have mean as 2, which means that this should have a parameter as half. Okay, so we had seen how to do this, how to generate an exponential or a Rayleigh distributed random variable from this. So we had seen that this theta can be generated using uniform random variable as rand of let's say I have want to generate n cross 1 dimension multiplied by 2 into pi, and this will give me from 0 to 2 pi. So I want to shift it by pi. So this will give me from minus pi to pi, and then I can generate this r as square root of exponential random variable, and exponential we can generate by minus 1 by lambda. Here lambda is half, so 2 into natural log or log of 1 minus rand n comma 1, like this. And then we can have my x1 as r cos theta. We can also have it as r sin theta. No harm, it will give same results. And once we have that, we can get our required Gaussian random variable again using the same formula which we had used earlier, that is mu plus sigma x1. So then we can have our x equal to mu plus sigma x1. So let's try to do this in MATLAB. Let's do it in the same code just to compare what is happening. So using rand. So for that, what we want, get r and theta, set x1 is equal to r cos theta or r sin theta, and so this will give standard normal, and then get x equal to mu plus sigma into x1. So let's do that. So we have this theta as rand of n comma 1 multiplied by 2 into pi, minus we need to shift it by to get from minus pi to pi, and then we have our radius r, which will be square root of minus 2 into log of 1 minus rand n comma 1, and then we have our x1 as mu plus square root, or let's say x11 as mu plus square root of sigma square into x11 as r into cos of theta, and x as mu plus square root of x11 into sigma square into x11. And then again we'll repeat the same thing. Okay, so I want them to be overlapped, so I'll write hold on. Then I'll just add legends. So the first one is using rand n, and second plot will be using rand. And just for sake that these have a darker line, I'll just add line width. So if you see, these both the plots are overlapping very nicely. So if you see, these both are overlapping nicely. There are little bit deviations which are because of the way we are plotting histograms and all those things. But that is okay. As we increase the number of realizations and as we fine tune the histogram bin, these two will be exactly same. Any questions in this part? So in this particular question, what we did is we saw how to generate Gaussian random variable with desired mean and variance. One using random, which simply generates a standard normal, and then we added mean and multiplied it by standard deviation. And another thing that we did was using rand function, that is generating it through scratch. Any questions? Okay, if there are no questions, then let me move on to the next question that I have. So this is a simple question. I just added it uh, for better understanding. It was done in the lecture also, but still I'll simply repeat the proof for Chebyshev inequality. So what is Chebyshev's inequality? So it says that if I have a random variable x, and if I take x minus mu, and probability of that to be greater than epsilon, then this probability is less than or equal to variance of x divided by epsilon square. And this x or this mu is basically expectation of x. This mu is expectation of x. So what we do is we start from the left hand side. So let's try and prove it for continuous random variables. So variance of x for a continuous random variable is simply x minus mu square from minus infinity to infinity fx of x dx. Okay. Now, if I look at a subset of this interval, that is this is basically my entire real line. Now, if I look at only a part of this real line, then that will give me a value which is less than this particular value that we are having. So if I restrict it only for those cases where my x minus mu are greater than epsilon, so this thing is a smaller set, and if I evaluate the same integral like this, x minus mu square fx of x dx, so this is only a part of the entire real line. So this is a smaller thing, smaller interval, and this is a positive thing, this is also a positive. PDFs are always non-negative, so this thing will be basically less than or equal to the original integral. Now another thing that we have here is this particular quantity here. So we are integrating it over a region where this particular quantity is greater than epsilon. Okay, so then we can write this as greater than or equal to epsilon square over the same region, x minus mu greater than epsilon fx of x dx. Now what is this? We are integrating the PDF over a small set or over a particular set, and this particular thing will basically give me probability that magnitude of x minus mu, or probability of that particular set, that is x minus mu, is greater than epsilon. This is by definition. Okay, so therefore what we have is this thing is simply epsilon square into the probability. So now we can rearrange and write probability that magnitude of x minus mu greater than epsilon is, we have this inequality, less than or equal to variance of x, and we have this epsilon square, which is again a positive quantity, so inequality won't change, upon epsilon square. Okay, so this is the small proof for Chebyshev's inequality. If you have any questions, then please let me know. Okay, if there are no questions, then let me move on to the last question that I had planned to cover today. So, okay. So let x1, x2 and xn be IID random exponential random variables with mean 1. Okay, and now what we need to do is we need to apply central limit theorem to observe the results from, and we want to observe the results from MATLAB. Okay, so okay, let's start. So what is given to us is xi's are exponential with mean 1. So mean of an exponential random variable. So if I have some xi's distributed as exponential as lambda, then expectation of xi's are 1 by lambda, and similarly variance of xi. So this is something that you can check, that is also 1 by lambda. Okay. Okay. So this is exponential 1, which means that expectation of xi is 1 and variance of xi is also equal to 1. And now we need to apply central limit theorem to them. Okay, so for that, what we need to consider is Sn. So this is Sn, and this Sn is simply summation I equal to 1 to n xi, and let's say we have a random variable Zn. Zn, which is Sn minus n mu by under root n into sigma. Okay, so here my mean, my sigma is basically, sigma square is 1 by lambda, but however now my mean here, my mean mu, so this is mu and this is sigma square. So this Sn minus, so this thing will be simply Sn minus n mu, that is n upon under root n. So this is something that we are having, and what we said is this thing will converge to 0, 1 as n tends to infinity. So this is how we'll be having a central limit theorem for exponential random variables. But now let us see if that thing actually follows using MATLAB. Okay, so for this what we need to do is we want to generate exponential random variables with lambda equal to 1. And then we need to figure out, we need to use the definition of Sn and Zn, and then see if it converges to Gaussian or not. So let's try to do it on MATLAB. Okay, so let me add So let's say I generate 10,000, sorry, 1 lakh samples to generate the PDF, and let's say I have n as, let's do this for n equal to 1 to 10 to 100. So let's do it for different values of n. And for that, what we will do, for each value of n, first thing that we need to do is we need to generate exponential random variables. And for that, so this x will be equal to, we want exponentials, so that we can obtain by considering minus 1 by lambda. So let me write a lambda here also, lambda equal to 1. So minus 1 by lambda into log of 1 minus rand n comma n. So what this will do, this will generate exponential random variables of dimension n comma n, and then I want to generate this Sn. So this Sn will be basically sum of x along the rows, because there are n rows and I want it for n Sn. Then I have this Zn as, again I'll write down this mu specifically, that will be 1 by lambda, and sigma square will be again 1 by lambda. So then I have this Zn. So this Zn is nothing but Sn minus n times mu divided by square root of n into sigma square. Okay, so this is what we will be having. Okay, so now we have this Zn, and what we will do is we'll generate another thing, that is Yn, which is Gaussian, just to check what is happening. So that can be done by considering mu plus s square root of sigma square, so sigma square by n, into square root, sorry, into rand n of n comma 1. And now let us do this x1 f1 x1, which is equal to histogram of Zn comma, let's say 100 bins, and then we have f2 x2, which is equal to histogram of Yn comma 100. And then what we can do is we'll plot, so we'll plot figure, plot x1 comma f1, hold on, plot x2 comma f2, hold off, legend will be sum of exponential, and then we have Gaussian. Okay, then we have, let's say we'll put a title also. So let's write it as central limit theorem, or CLT, for n equal to num to str n. Okay, so now let's see what happens, and it's for fun we'll add one more thing. Pause. So let's run this. Okay, there is some error, suppose. Okay. So if you see, it's coming something weird for n equal to. Let me just add line width. Okay. Yeah, so this is for n equal to 1. Then if I add for n equal to 10, I think there is something wrong. There is something wrong. Sorry, this should be simply standard normal. I have already normalized it. Extremely sorry. Yeah. So this is something like this for n equal to 1. Then for n equal to 10, it slowly starts to overlap. N equal to 11, sorry. Then for n equal to 21, again it starts more and more closer. N equal to 31, again it overlaps more. 41, then 51, 61, it's overlapping more and more. See 81. So it just goes on, the overlap slowly starts to get more and more. So that is how the CLT works. So I think we have very less number of samples. So if we increase the number of samples, let's say to 7, then this is for n equal to 1. Then this is for n equal to 11. So these will take time. This is for n equal to 21. This is for 31. So these take time because the number of realizations are very large. N equal to 41. So there will be slight deviation because these are approximations. Okay, so this n equal to 51 was taking a lot of time. Okay. Yeah, so that n equal to 51 takes a lot of time and it's not possible to take it. My PC gets my PC hangs if I go for higher values. So let's, hello, hello. Okay, so this n equal to 51 and takes a lot of time and it just makes my PC hang. So let's not go for it. But if when we saw it for n equal to 5, n equal to 10 raised to 5, and for all the values of n equal to 1 to 100, we were able to see how the CLT is working. So that's how central limit theorem will work. So this exponential random variable, even if it has only positive support, slowly it starts approaching to the standard normal or standard Gaussian. Slowly, it won't be exact, but it will be slowly starting approaching the standard Gaussian. Any questions? If you have any questions, then please let me know.
What is Rayleigh distribution?
Sorry,
Is Rayleigh distribution?
what is Rayleigh distribution?
We have plots from Rayleigh.
Sorry, I'm not getting your question. Can you type it in chat box? Your voice is cracking a lot.
Okay.
Yeah, yeah. Please type it in chat box. I'll answer. Please type it in chat box. Here, if Nidhi, please type it in chat box. I'm not able to hear what you're saying.
What is Rayleigh distribution?
What is Rayleigh distribution? That you're asking?
Yes, yes.
Okay. Okay, let me add a page. Okay, so Rayleigh distribution, if X is Rayleigh with parameter, let's say sigma, then its PDF fx of x will be equal to, or let's start with CDF. CDF is easy. CDF fx of x is equal to 1 minus e power minus x square by sigma square for x greater than or equal to 0, and its PDF fx of x is equal to 2x by sigma square into e power minus x square by sigma square for x greater than or equal to 0. So these are the PDF and CDF. These are definitions of a Rayleigh random variable. However, when we are having a circularly symmetric complex Gaussian, let's say z equal to x plus jy, this is circularly symmetric complex Gaussian. Then magnitude of z, which is equal to under root of x square plus y square. This follows Rayleigh distribution with some appropriate parameter. I'm not mentioning what parameter for now. But yeah, this follows Rayleigh. So this is the significance. So this circularly symmetric complex Gaussian will show up multiple times in when we are doing wireless communication. And when we have the envelope of this circularly symmetric complex Gaussian, or if we take the absolute value of that random variable, which is circularly symmetric complex Gaussian, then we get a Rayleigh distributed random variable. This is the definition for Rayleigh distributed random variable, and for wireless communication, I just mentioned the significance of it. Is it clear?
Yes, ma'am.
Okay. Any other questions? Uh, Regarding assignments, I am not the one who takes care of assignments. Please post it in the portals. I don't have access in evaluating your assignments and other stuff. Please write in the discussion portal, or you can also write to the NPTEL people. These people will take care of it. Last time also, when there was some issue with assignments, please mention it in portal. They will take care of it. I don't have access to it and I can't do anything with the assignments. But yeah, if you post it in that portal, they will help you out. So sorry, I mistakenly left the meeting. If you have any other questions, please ask. I think Nidhi has raised her hand. Please ask your question.
No other question.
Okay, okay.
Thanks very
So,
much.
okay. If there are no further questions, then you're free to leave the meeting. Thank you for attending today's session.
Thank you, ma'am.